Somewhere inside this image, there are planets that no one has discovered yet. Not just one planet, not 10, but possibly hundreds, perhaps even thousands. Hidden among more than 60 million stars, buried within the glowing dust and impossible crowding of the Milky Way's central bulge, Euclid has captured something that looks like a masterpiece but behaves like a cosmic trap. At first glance, it is pure beauty, a vast, glittering window into the crowded heart of our galaxy. Stars are packed so tightly that the image almost stops looking like space and starts looking like fire. Nebulae glow through curtains of dust. Star clusters are buried deep in the background. The field is so densely populated that even the software designed to process space images struggled to understand what it was seeing. But this is not just a photograph. It is a before picture, a time capsule, a reference frame that future astronomers will use to catch planets as they briefly reveal themselves through gravity. In the center of our galaxy, the stars are so crowded that, every so often, one star passes almost perfectly in front of another. When that happens, gravity bends the background light, magnifying it like a cosmic lens. If the foreground star has a planet, that planet leaves behind a tiny spike in the light, a hidden signature, a brief distortion, a planet appearing without ever being seen directly. Euclid did not simply photograph the core of the Milky Way. It may have created the map that will allow us to find the invisible worlds hidden within it. Euclid was not designed primarily to observe the bright center of our galaxy. Its main mission is far larger and far darker. Euclid is a dark universe telescope built to map billions of distant galaxies and help scientists understand dark matter, dark energy, and the large-scale structure of the cosmos. Normally, it studies deep, relatively dark regions of the sky where its sensitive instruments can measure faint galaxies without being overwhelmed by nearby brightness. For this observation, however, Euclid did something unusual. It turned toward the light. It pointed directly at the galactic bulge, the intensely crowded inner region of the Milky Way where stars are packed together in enormous numbers. This is one of the most difficult places in the sky to image because the density of stars is extreme and the brightness can overwhelm instruments designed for precision. Yet that very difficulty is exactly why the region is so valuable. If you want to discover planets using gravitational microlensing, you need stars, an enormous number of them. Microlensing depends on a chance alignment. A foreground star must pass almost exactly in front of a more distant background star. When this happens, the gravity of the foreground star bends and amplifies the background star's light, creating a smooth, bell-shaped brightening that can last for weeks. If the foreground star has a planet, that planet adds its own tiny gravitational distortion, a small spike, a brief anomaly, a subtle signal that something unseen is orbiting there. These alignments are rare. Across most of the sky, the odds of witnessing one are extremely low. But toward the center of the Milky Way, the incredible density of stars changes the game. So many stars are led along the same line of sight that the chances of capturing microlensing events become dramatically higher. That is why Euclid's image is so important. It is not simply a beautiful portrait of the galactic center. It is a hunting ground, a field containing more than 60 million stars, captured with enough precision that future changes in brightness and motion can be compared against it. Euclid has given astronomers the baseline, the still frame that exists before the galaxy begins revealing its hidden planets. Most people are familiar with the transit method of finding exoplanets. A planet passes in front of its host star, the star dims slightly, and astronomers measure that tiny dip in brightness to infer the planet's presence. It is an elegant technique, but it has limitations. The planet's orbit must line up almost perfectly with our point of view, and the method works best for planets orbiting close to their stars, especially those that transit repeatedly. Microlensing is different. It does not require a planet to pass in front of its own star. It does not require repeated transits. It does not even depend on detecting the planet's light. Instead, it depends entirely on gravity. When a foreground star crosses the line of sight to a background star, its gravity warps space itself. Light from the background star bends around the foreground star, making the background star appear temporarily brighter. This brightening follows a predictable curve. But if the foreground star hosts a planet, the planet's gravity creates an additional disturbance in that curve. A small, uneven spike appears for a brief moment, revealing a planet that might otherwise remain completely invisible. That makes microlensing uniquely powerful. It can detect cold planets far from their parent stars. It can discover worlds at distances where transit surveys struggle. It can reveal planets too faint to be directly imaged, and it can uncover planetary systems that would otherwise remain hidden within the dense star fields of our galaxy. There is, however, one challenge. To interpret a microlensing event correctly, astronomers need to know exactly what the stars looked like before the alignment occurred. They need a baseline. They need accurate measurements of the star's positions, brightness, and separations before gravity briefly transforms the scene. That is precisely what Euclid has now provided. Its 26-hour observation was not long enough to discover planets directly through microlensing, since these events often require monitoring stars continuously for more than 20 days. Instead, Euclid captured the ultimate pre-event image, a sharp, wide, high-resolution reference of the exact field that the Nancy Grace Roman Space Telescope will later monitor. NASA's Roman Space Telescope is expected to begin searching for microlensing events in this same region in the coming years. It will repeatedly observe this patch of sky, watching stars brighten and fade as gravitational alignments occur. When Roman detects one of these events, Euclid's image will become the past, the before picture, the comparison frame that allows astronomers to confirm